Hi, this is Kevin, and this is my project 3 for Dr. Hassan Rashidi's course, Design and Manufacturing. So, for project 3, we are to choose 5 manufacturing topics from the course material or the course textbook. Manufacturing Processes for Engineering Material by Sarop Kalpakshian and Stephen Schmidt. So, the 5 topics I have chosen are friction welding, explosion welding, lithography, processing superconductors, and printed circuit board. Friction and explosion welding are chosen because of their interesting techniques to weld materials, while lithography and printed circuit boards are chosen because they are important for producing electronics that are vital to the world today. So for friction welding, uh, you are to generate heat through friction between the two workpieces, unlike other welding techniques which usually uses heat to melt the material to join them. On the figure to the right, you can see that one piece is stationary while another piece is rotated, and an axial force is applied to them to cause them to come into contact and cause friction, which generates heat. The force is increased to remove the gaps between the two pieces, and the rotation is stopped to allow the contact point to solidify and join the two pieces together. This process allows the two materials to keep their material properties while fusing them together. I think this topic is interesting because it utilizes friction, which you usually want to reduce in a system. Like in a car engine, you don't want friction so that the engine runs better and uses less fuel. But in this case, you use friction to combine two materials to achieve the composite material that you want. And for the capabilities of friction welding, it can join two metal materials that usually can't be joined with by heating, since it might ruin the material property when you heat up the material and let it cool down. However, friction welding requires the material to be solid, so ring would unlikely work because of the gap that it could cause, and also the material needs to be symmetrical because non-symmetrical materials might cause gaps, which makes the joint weaker. Additionally, pieces with sharp edges like square and rectangles are stress concentrators, which might cause the material to break due to torsion, which is why it is usually limited to cylindrical materials. And additionally, friction welding requires large and heavy machineries, and the joints are really hard to control compared to other welding techniques. The next topic is explosion welding, which uses a flyer, the metal that you want to join to the base plate. A clearance gap is formed between the flyer and the base plate, while an explosive charge is placed on top of the flyer. Once the explosive is detonated, the base plate and the flyer would have immense amount of pressure, which allows them to bond. This causes plastic deformation on the contact point, and the high pressure allows the atoms to bond with each other. On the figure on the bottom, you can see that there are two different types of explosion welding, one with a constant clearance gap, while the other one is angled. These are used depending on the different materials that you want to join, or based on the final property you want the composite material to be. I chose explosion welding because explosion is usually perceived as a destructive method, but in this case it is constructive since it is used to form a material to combine the two properties of two different material. For explosion welding, it can join two metals while preserving their property since you don't use heat to join the materials. However, explosives are incredibly dangerous, so they're highly regulated, and they're also limited to flat surfaces to reduce the possibility of gaps when joining the material. The next topic is lithography, which is used in making electronic components, such as in the CPU. So, a mask or a reticle has a pattern on it which you would use to apply to a substrate, which the substrate is usually made of silicon. In the figure to the right, you can see that there are 4 different techniques to apply the mask pattern onto the substrate, one using light, one using electron, X-ray, and ions. These techniques are chosen depending on how wide you want the inscribed pattern to be. Usually the pattern is bigger than the chip, and to apply the pattern onto a smaller chip, you will use something called reduction lithography, which uses lens to focus the pattern on the silicon wafer. I chose lithography as a topic because CPU allows us to have high computation power and collect a lot of data, and I believe that lithography will continue to be used in the future to improve the chips. And what's even more interesting is that the current CPU can fit millions of transistors on it, and it is thanks to lithography that we can achieve something like this. The advantages of lithography is it's good for printing in high volume, but it needs a clean environment since any contaminants in the air, such as dust and dirt, can cause defects on the product. The 4th topic I'm going to talk about is processing superconductors. So superconductors are materials that can conduct direct current with little to no energy loss. And to make them, you need to make a powder, usually with metal or ceramic, and you have to mix and grind them to reduce their grain size. Once you reduce them, you would shape them and then heat treat them to allow the grains to align properly, which gives them the superconducting property. On the bottom, you can see one of the techniques to shape and make a superconducting wire using a technique called powder and tube method, which you would fill the ceramic powder inside a cylinder and you would pack it, and then you would extrude and draw out the cylinder into a wire. I chose this process because it is interesting to see something that can perform at around 100% efficiency. It is usual in systems to not perform at 100% efficiency due to losses such as friction and energy loss to sound and other losses. So it is really interesting to see that you can conduct and transfer electricity with 100% efficiency. Superconductors are useful in energy transport, storage, and generation. However, the materials are really difficult to process. And metal superconductors, to give them the superconducting property, you have to operate them at really low temperatures, which is really which is lower than 0 degrees Celsius, which might be expensive or difficult to maintain. Or ceramic superconductors, which can sometimes operate at ambient conditions. Ceramic is really brittle and anisotropic material, so the grain size is really difficult to align. You need the grain size to align properly to have the superconducting property. For the last topic, it's printed circuit board. Printed circuit boards are really important for electronics as it's a medium for integrated circuits, electronic components like resistors and capacitors, and connections to be on. The board is usually made of epoxy resin, and it is reinforced with epoxy or glass to make sure it's stiff and rigid. On the figures to the right, you can see that the PCB has internal tracks and also external tracks with holes to allow integrated circuits or resistors to connect the tracks. These tracks allow the PCB to be compact and allows the connection to be reliable. However, it's at the cost of high manufacturing costs, and also it's really hard to iterate between multiple designs for a PCB. I chose PCB because I've built electronic circuits with breadboard, and seeing it in a more compact and more cleaner and easier, better connection form is really interesting to me. Thank you, and here are my resources used.